Colonizing the Moon.
The Moon is the closest celestial body to Earth, and so far, it remains the only place beyond our planet where humans have ever set foot. The last crewed mission left the lunar surface more than 45 years ago, yet today, interest in further exploration of Earth's natural satellite is once again rapidly growing. Why has the Moon returned to the center of humanity's attention? Modern robotic missions exploring planets and small bodies of the solar system are making one thing increasingly clear. Space exploration is no longer science fiction. It is a real and achievable goal. And more importantly, it may offer tangible benefits in the foreseeable future. Among all objects beyond Earth, the Moon is considered the most accessible target for human expansion in the coming decades. The surface of the Moon represents a potential source of mineral and energy resources essential for sustaining life and advancing technology. Lunar soil contains rare Earth elements whose extraction on Earth is often associated with serious technical and environmental challenges. It also includes unique metallic compounds that do not occur under terrestrial conditions. Yet the Moon's greatest wealth may not be metals at all, but gases, hydrogen, helium, and their isotopes. Among them, one stands out in particular, helium-3. This light, inert gas is of exceptional interest for the energy systems of the future. If controlled nuclear fusion becomes a practical reality, reserves of helium-3 could provide an almost inexhaustible and environmentally clean source of power. Helium-3 is embedded in the lunar regolith, a layer of finely fragmented mineral material that covers the Moon's surface. Its highest concentrations are found in regions where the soil is rich in titanium oxide compounds. When lunar regolith is heated to temperatures of around 200 degrees Celsius, hydrogen begins to be released. Once separated, this hydrogen can be used as a component of rocket fuel. To extract all gases more completely, the regolith must be subjected to even higher temperatures. Processing a single ton of lunar soil can yield nearly 100 grams of hydrogen, about 50 grams of helium-4, and water vapor. At first glance, these quantities may seem insignificant. However, when used in a thermonuclear reaction with deuterium, a heavy and stable isotope of hydrogen extracted from Earth's ocean water, they can generate approximately 2.6 megawatt-hours of electrical energy. That is roughly the same amount of energy produced by a standard 1 gigawatt nuclear power plant in just 10 seconds of operation. According to expert estimates, the industrial development of the Moon could begin no earlier than 2025 and may continue for several decades. Even so, preparation for this process is already underway. Over the past 10 years, large-scale scientific and technological programs have been actively implemented. In fact, we are now witnessing the first phase of lunar development, the research phase. During this stage, detailed mapping of the Moon's surface has been completed. Its gravitational field has been studied, along with its extremely thin gaseous envelope. Particular importance was placed on the L-Cross mission, which deliberately impacted a probe into the Cabeus crater near the Moon's south pole. The results confirmed the presence of significant deposits of water ice and frozen gases at the bottom of the crater. The next step will be the exploration of mineral deposits, both from lunar orbit and with the help of automated landers. At the same time, scientists will identify the most promising locations for future crewed landings. It is in these regions that the first long-term human bases beyond Earth may one day appear.
The colonization of the Moon will require enormous financial resources and significant effort. Nevertheless, the key technologies needed to make it possible already exist and could be deployed in the foreseeable future. According to expert estimates, this may happen within the next 10 to 15 years. So what exactly do scientists propose? First of all, the creation of experimental facilities for the extraction and primary processing of useful minerals. This also includes the development of systems for continuous monitoring of the lunar surface, as well as precise positioning and control of technical devices and lunar rovers operating on Earth's natural satellite. A separate and equally important direction is the development of transportation systems capable of ensuring efficient travel between Earth orbit and lunar orbit. Next-generation mobile platforms will be equipped with instruments for collecting and analyzing samples of lunar soil, along with autonomous control systems that include sensors for monitoring environmental conditions and surface terrain. In terms of design, these vehicles will largely resemble existing lunar and Martian rovers. They must combine high mobility with a substantial operating range, while being powered by relatively low energy sources such as solar panels, chemical batteries, or radioisotope generators. All collected data will be transmitted to orbital spacecraft and then relayed back to Earth. Based on this information, specialists will be able to identify specific regions best suited for the initial test extraction of resources or for the placement of the first elements of a lunar settlement. The final stage of lunar exploration involves the large-scale use of the Moon's resources. This includes not only the extraction of raw materials, but also their processing directly on site, as well as the construction and life support of permanently inhabited lunar bases. This stage is unlikely to arrive anytime soon. However, humanity already possesses the necessary prerequisites. Above all, this includes decades of experience in long-duration crewed space missions and the construction of large pressurized structures in Earth orbit, such as the Mir space station and the International Space Station. At present, the most significant achievements in lunar orbital monitoring belong to the United States and Japan. As early as 2007, Japan launched the Kaguya spacecraft into lunar orbit, accompanied by 2 sub-satellites, Okina and Onna. At the time, this mission became the most ambitious lunar exploration program since the legendary Apollo era.
Today, as part of preparations for the future colonization of the Moon, active development is underway of technical systems intended for its industrial exploitation. One such project involves a self-propelled technological vehicle mounted on a tracked chassis. Its design includes a cantilever-mounted panel equipped with heating elements. Under their influence, a mixture of gases is released from the lunar regolith. This mixture is then fed into a cooling unit where it is separated into fractions according to their different boiling points. After separation, hydrogen and helium-3 are directed into separate storage containers. Heating elements with a surface area of approximately 2 square meters are capable of raising the temperature of about 1,200 kilograms of lunar material to 450 degrees Celsius, consuming roughly 420 megajoules of energy in the process. During the lunar daytime, this energy can be supplied by a power system with a capacity of around 20 kilowatts based on solar panels. Operating in this mode, it is possible to obtain approximately 60 kilograms of hydrogen and up to 10 grams of helium-3 over a period of 28 Earth days. The extracted materials can then be used in different ways. Some will be loaded into containers aboard spacecraft returning to Earth, while hydrogen may be pumped directly into the vehicle's fuel tanks. At the same time, industrial-scale systems designed for large-volume extraction of resources from the regolith and lunar subsurface will require far more energy than experimental units. For this reason, they will most likely need to be equipped with nuclear power systems, as solar energy alone would be insufficient for such operations. In essence, only one major task remains: to unite the efforts of humanity and direct them toward practical implementation of projects that may ultimately prove not only technologically feasible, but also economically viable. And you already know what to do if you don't want to miss the next episode. Liking the video and subscribing to the channel costs nothing, and there is much more interesting content ahead.